Hello and welcome to the live stream. I'm Andy, and tonight we're talking about some navigation math and all kinds of different kind of formulas and stuff like that that we'll look at. And you might be thinking, hang on a minute, I'm not good at math. Oh, I missed the, hang on, hang on a minute, there we go. I'm not good at math. What do you mean we're talking about math tonight? I don't like math. And that's okay. And that's one of the most common things that I find is as soon as we stick a number on the whiteboard, sometimes people kind of look and they go, "Oh no, here we go!" Right? So definitely say hi in the chat and poke me in the chat if you're looking at something and you're like, I don't know what this is about. For sure, because that's what it's all about. And I think that one thing that can be really helpful for that, if you're like this guy who's like, I don't know what's going on, looking at the problem 3 or 4 different ways, I find can sometimes help, and really understanding not just the numbers that are down on your page, but looking at kind of the problem and how does it work, and even if you didn't get the exact right number, do you have kind of a sense for what it is that we're trying to solve and that sort of thing. So that's my goal tonight is to not make you think like this guy, but to have you thinking, yeah, I can understand what that problem is and what we're doing. Probably a bit of a shorter one tonight, but a couple things to chat about. So what I want to start with tonight is getting back on track. So this has to do with a lot of test questions. We'll ask you something about, hey, you were on track and now you're off by this much, and how do you get back? And so I want to look at, there's kind of 2 different methods that we'll look at here. So the first method has to do with you're in the first half of your route. Let's say you're flying from airport A, you're going to go to airport B, and you recognize that you're off track. You realize, okay, along my route, I saw in my map that there's a little lake over here, and I see that my airplane, oh, it's not updating, hang on. Hello. My drawing. Oh, it's the other computer. Hang on. Cannot draw. Need to be able to draw. Okay, plan B. Okay, so we're over this kind of lake over here somewhere, and we identify a landmark that we are off track, and we know approximately how much we're off track because we found some landmark. So the first method we'll talk about is called the opening and closing angles method. And I just realized, there we go. So the opening and closing angles method is what we'll talk about first. So you recognize, okay, I'm over this little lake over here. How do I get back from this lake to being back on track? So the opening angle in the opening closing angles method is, well, we started at A and we ended up in this other position. Say we identify more specifically, we're right here. So this angle here, the angle between the track that we wanted to fly and the track that we're actually on, that's called the opening angle. So that's the opening angle in the opening and closing angles method. The other angle is from the destination to our position. If we were to fly directly to the destination, that would be the closing angle right there. So the opening angle here and the closing angle here, the opening and closing angles method. So it's quite simple math-wise to figure it out. If you know this number here and you know this number here, what the angles are, you can just add the two together. So let's say, you know, in this case, maybe not to scale, of course, but maybe we're 10 degrees off track here. And then from this position to the destination, maybe that's 5 degrees off track. So if you identify all those things, then now you know how to get back on track. Now we need to change our heading by 15 degrees. So you add the opening angle to the closing angle, and you get 15, and that's the change you would make. So in this case, let's say that our heading was due north. Subtract 15 degrees off of that, so that's going to be 345. Yeah, 345 degrees would be our new heading to fly, and that would get you to the destination directly, right? So that again is called the opening closing angles method. And I think I lied at the very beginning. This one can be used anywhere along the route. So it can be used in the first half, second half, wherever along the route that you like. So that's the convenient thing about the opening and closing angles method, is it's not specific to any particular place in the route. The nice thing about it too is it gets you directly to the destination, so you don't have to worry about getting back on track and then continuing to the destination. The other method is called the double track error method, and I may have mentioned that. So the double track error method is the one that only works in the first half of the route. So the reason being is because what we're going to do is look at the position that we're off track. Say we ended up over this point, and what we're going to try to find this error and basically double that track error to get back on track in the same distance from the departure point. So let's say we flew for 5 minutes. By the time 5 minutes comes up again, we should be back on track, right? So how does this work? Well, we still have this opening angle here. So let's say in this case we have a 5 degree opening angle. So knowing that that's 5, we can double that, the double track error method. So this here is our track error. So we double that. So instead of adding 5 degrees to our heading, we're going to add, or in this case subtract, because we're going left, we're going to subtract 10 degrees from our heading. That'll get us back on track. Once we get there though, we don't want to keep going and go through our track to the other side. So then we would add 5 degrees back. So think about if we took our track error here, so we're off track about 5 degrees. The way to understand this problem is we're off track 5 degrees. Think about why. Why did we get off track 5 degrees? Because we did our planning. We presumably filled out some kind of nav log, and we planned ahead, and we knew, okay, we're going to fly 360 degrees, and that should take us there, but we're 5 degrees off. Why would we be off? Well, it's probably something like the wind, right? The wind can blow you off track. So if we're 5 degrees off track, yeah, exactly, Alex got there. So if we're 5 degrees off track based on the wind, if we just looked at this track error and took off 5 degrees, we're not going to fix anything. We're going to parallel our track, and that's not very helpful. So this is the reason why we double the track error. So we see the 5 degrees track error, and instead of subtracting 5 degrees, we're going to subtract 10 degrees. That should get us back on track, and that'll get us back on track in the same time or distance that it took to get to this point along our route. Then we will get back on track after that. So then that's why once we get back on track, we need to make another correction again, because we're using more of a correction than would keep us parallel. So earlier, if I just made a 5 degree heading change, that would have kept us parallel. So great, I will make a 5 degree heading change compared to our original heading. Now, one thing I wanted to kind of look at with these problems, because I just threw a lot of terminology out there, kind of assuming maybe you've heard it, you know, a little bit here and there. But I want to define some terms here a little bit. So this black line here from A to B, that's what's known as our desired track, or our required track, you might hear it called. So that is, or even intended track, I've seen as well. That's the track that we have planned and want to fly. The track made good is this blue line here. Oddly enough, because it's not good, it's not what I want, but that's what they call it. Also called course, yeah. The track made good is actually our track made bad. It's the line that we actually flew over the ground is our track made good. And so that would be this blue line here. And then track error is, of course, the angle between the two. So I was saying that this one can only be used in the first half of the trip, so I want to show you that. So let's say we end up out over here. In this case, we have you know, a track error. Let's say, I don't know, that's 15 degrees. So we're off by 15 degrees. If I double that track error, the problem is if I subtract 30 degrees from my heading, I will get back on track after flying this distance again. And the problem is that's more than it will take to get to my destination. And so what's going to end up happening is I'm going to end up getting back on track way off the you know, we're well beyond the actual destination. But even further than that, it'll probably be like something like this. We'll go past the destination. You might see it go by, but you're not going to get back on track by the time you get to the destination. So that's no good. So this scenario would be one that calls for the opening and closing angles method. So again, I'll take my 15-degree opening angle. This looks like well more than 15 degrees in this case for this closing angle. So I don't know, maybe that's 20 degrees or whatever. We're getting to quite big numbers, but you would add them together. So let's say this one was 20 degrees. Well, then now I'm going to change my heading. In this case, again, to the left, I would subtract. I would go 35 degrees to the left, and that should get me back on track. So that's the two methods here. Now, how you would prepare your map for that can be quite important, especially for longer trips. So that's why people suggest use 10-degree drift lines. So how that would work is you have from your point A here, you would look at the map and you would draw out little 10-degree drift lines like this with your protractor and get them all nice and accurate and better than I did. And then you would look at point B, and then you draw 10-degree lines out like this as well, and they're gonna intersect somewhere near the middle point on your route, and that way you can kind of guesstimate what these opening and closing angles are going to be. If my airplane ends up right on the line right here, well, I know I'm at 10 degrees error, 10 degrees off of my desired track, so a 10-degree track error from point A. But it's not quite 10 degrees from point B, because look at where this 10-degree drift line comes off here. We're maybe 6 degrees track error from point B. So the closing angle about 6 degrees, opening angle would be about 10 degrees. So if you wanted to use that opening closing angles method, you would use 16 degrees. If you wanted to use the double track error method, you would use 20 degrees, and then that would get you back on track. Oh, maybe about here you'd get back on track, and then continue to the destination with 10 more degrees. So those are the two main methods that you might get test questions on that. How do you get back on track for those? So not too much math-wise for those, but I do think that they're they can be a little bit tricky because you do have to keep straight in your mind kind of where do you add the numbers and that sort of thing. One that's a little more tricky math-based get into here is the 1 in 60 rule. Just preparing my map here. Okay. So, for the 1 in 60 rule, this is one that it's a couple more numbers. There's more numbers on my page at least, and that can tend to make people go, "Oh no, I don't know about this math thing," but it's okay. I got a cool trick, and I have two different ways that I want you to look at the 1 in 60 rule to keep you out of trouble. So, what is the 1 in 60 rule? The 1 in 60 rule is if I am 60 miles downrange, 60 miles along my route, and I'm 1 mile off track, then I should be 1 degree off track. That's the 1 in 60 rule. And so let me get this going again. Okay, so I have my point A and point B here. So if I was, let's say point A to point B is exactly 60 miles. It's not letting me draw a standby. Okay, point A to point B is 60 miles. When I get to point B, again, if I'm here instead, if that's 1 nautical mile off track, then that opening angle is going to be 1 degree. So that's the 1 in 60 rule. Now, it's not always 60 miles and 1 mile and 1 degree. So where the tricky part comes in is how do you figure it out when the numbers aren't 1 and 60. So let me give you another example. Let's say that this distance from A to B is 120 miles. And let's say when I get to B, I'm at this point and it's 2 nautical miles off track. What's the track error? How many degrees off track am I? So I'll show a mathematical method in a bit to solve this. But I think you'll find for this sort of scenario, it's easier to not think about the math, at least for me. It's easier to just look at it and break it down into intervals of 60. So in 120, that's 60 and then 60, right? So if I cut this route right in half, I've got 60 miles here, and I got 60 miles here. So then at point B here, I'm 2 miles off track, but halfway there, I'm going to be at this spot, and I'll be 1 nautical mile off track. So after 60 miles, I'm 1 nautical mile off track, 1 in 60, right? So the track error for this problem is still 1 degree. Right? So 120 miles, 2 miles off track. It's actually 1 degree off track. Let me show you my second method to look at this problem, which is more mathematical. And so the way I would encourage you is to maybe even do the math part first, and then do what I just did there to kind of reality check. Does that make sense? So here's the math part. So we've got 1 in 60, and then we had 2 in 120. Now, I want you to take your head, tilt it 90 degrees this way, and turn that those 4 points, turn them in your mind 90 degrees. We're going to take this one up here and we're going to delete it, and we're going to make an L out of the other ones. So bear with me. We're going to have 60 over 120, and then 2. So we've made an L like this. So we took 60 there, we rotated 90 degrees, so it went up. We took 120, we rotated 90 degrees, so it went sideways. And we took the 2, we rotated 90 degrees, so it went down. And we made an L with it. And now we just have to solve that problem. And please use a calculator, because I'll use a calculator, because I'll be the first guy to mess it up. So I'm going to take my 60 divided by 120. I get 0.5, or half. And then that multiplied by 2, and I get 1, right? So that's our mathematical method for the same problem. I'm taking the 60 divided by the 120. That's very similar to what we were doing when we were just looking at it, on paper, looking at that root. We have 60. We have 2 intervals of 60, which makes sense. So so 60 is half the root, right? And that's why we're having the output number, having the miles, and getting the answer of 1. Okay, I'll clear this all out, and let's look at another example. So in this example, I want to look at you are 1 nautical mile off track. Just fighting with my mouse. There we go. You're 1 nautical mile off track after having traveled 30 nautical miles. So I'm going to start with the mathematical method, and then we'll reality check it in a second. So again, I'm going to start with 1 over 60, because that's the rule. And then 1 over 30. Take that in my brain and turn my head 90 degrees sideways. I'm going to get 60, 30, 1. Right? And I don't need the last number there, the 1 and 60. I don't need the 1 for that number. So 60 divided by 30, that's 2. 2 times 1 is 2. So the answer is 2 degrees off track. Let's reality check that for a second. We've got point A. We fly 30 miles, 30 nautical miles, and we end up 1 mile off track. What if we were to fly 60 miles at that same angle, that same amount off track, right? So if I keep on going, now I add another 30 miles. I'm not going to be 1 degree off track in this case. I'm not going to be 1 mile off track. I'm going to be 2 miles off track, right? So now 2 miles off track, out over here. After 60 total miles traveled, 1 in 60, that's going to be 2 degrees. So kind of 2 different ways to look at the same problem. So on a test, I would do both of these, right? And if you misremembered one or something like that, that would then point it out to you and be like, hang on, something's not quite right. Okay, let's look at another example here. Okay. So let's say we're 4 nautical miles off track. And we've traveled 120 nautical miles. So I'll start with the formula again. 1 over 60, because that's the rule. And then we had 4 nautical miles after 120. And the way that I know how to position this is of course 1 over 60. I just write it down on the page first because that's the rule. And then I put the 4 over 120 because that is formatted the same, right? So number of miles off track versus miles traveled, right? Okay, and then take your head, turn 90 degrees sideways, turn that picture 90 degrees. We're going to get 60 over 120 times 4. 60 over 120, that's 0.5, that's half. Start with that. 60 over 120. Every time I hit 0, it changes my screen. Sorry about that. So that's half. And then times 4 is 2. 2 degrees off track after this scenario, after 120 miles. Again, let's come back and reality check that. So we're at point A, and to point B. And that trip is 120 miles. They tend to do it like this. They don't tend to give you like odd, weird numbers that aren't multiples of 60 or in some way. So, you know, it doesn't tend to be like after 133 miles, they don't tend to be that goofy with it on test questions, but theoretically they could. But you know, in that case, I fall back to, well, it's multiple choice. Take a guess. You're probably pretty close. But anyway, so 120 it goes into, or 60 goes into 120 twice. So there's 2 60s in this route. And so if after so 120 miles is the whole trip, rather, after 120 miles, if we are 4 miles off track, then after 60 miles, the first 60 miles will only be 2 miles off track. And then again, that's 1 in 60 rule. 60 miles, 2 miles off track, that is a 2 degree track error. So there you go. So that's the 1 in 60 rule, kind of 2 different ways to look at it there for you. Okay. What I want to look at now is you might look and go, this isn't a formula, but bear with me. I want to look at cruising altitude orders, because it's one that there are some numbers in it that can catch people off guard. So cruising altitude orders say that on some headings we should be at certain altitudes, and at other headings we should be at other altitudes. You know, obviously we'll be flying in cruise and flying longer distances for navigation stuff, so it definitely applies in this scenario. So the way that it works is for easterly headings, and I'm going to start with the VFR rules. So for easterly headings, we're going to be odd thousands plus 500 feet. So it might be 3,500 and then 5,500 and then 7,500, for example. On westerly headings, it's going to be even thousands plus 500. So it could be 4,500 and then 6,500. Those ones tend to be ones that most people will be able to to remember if they look at it a little bit. But what gets people on the test question is Transport Canada will ask, you're flying at, you're after departure at this airport, and you're flying to this other airport, and the heading that you're flying will be like 181 degrees, right? And then you have to know, how do you actually know which number to fly? That's what tends to get people on the test questions. And so we have to know what the cruising altitude orders are based on. And so I'm going to speak very local to us here, southern domestic airspace. The cruising altitude orders are based on magnetic track. So I said you're flying 181 degrees. Let's look at those numbers first. So cruising altitude orders for easterly headings, that starts at 000 and goes around to 179. That is your easterly headings. And then from 180 around to 359, those are your westerly numbers. So you might think, okay, 181, that's in here somewhere. We should be using a westerly number, so we should be in even thousands plus 500. But it's tricky because I mentioned track. We're basing it on magnetic track. So track, just like we were talking about earlier, required track or track made good, all of this is where the airplane's actually moving over the ground. And so people get themselves into trouble on test questions because they put in what direction the airplane's pointing, the heading, right? I'm heading 181, but you can't actually answer this question without more information, without the wind, right? So if you had a wind that was out of the west that was sufficiently strong, you might actually have a track that is easterly. And in that case, now you need to be using the odd thousands plus 500. Gets even more tricky. There's one more layer to this. When do these start to apply? Because they're not all the time. It's not, from the moment that you lift off that you have to comply with this. It's not even all the time, when at some point you're going to have to climb and descend, right? So climbing and descending is okay. This is just when you're in cruise. But there's only certain circumstances that this is going to take effect. So the biggest thing to know is the altitudes that it is required to follow these. And where people get caught on test questions is what the regulation says is above 3,000 feet AGL is when this applies. And if you forget the AGL part, above ground level, then it gets real confusing because you might think, okay, 4,500, you always have to comply with the cruising altitude orders. But if your ground's at 4,000, you're not going to be required to fly at 4,500. Once you're too close to the ground, cruising altitude orders don't apply. So that would be the tricky test question. And the way that they lay it out is you have A, B, C, D for your possible answers. A and B might be the wrong direction ones. Maybe there's wind as part of the question. You got to figure it out. So A and B would be like the wrong directions. And then C would be, say, 5,000 feet. Well, the problem with 5,000 is if we're VFR, we can't fly at 5,000 in cruise because that is an IFR altitude, assuming that these orders apply. I wouldn't be able to fly at 5,000 because the IFR guys don't add 500 feet. So that wouldn't be the right answer. And then like answer D would say 3,500. And you go, well, 3,500, that's above 3,000. And so let's say in that case that wasn't the right direction. If you're actually going west and the answer said 3,500, you might think, oh, that's not the right direction. So that's wrong. But if the ground was at 1,000, you could fly at 3,500 because you're not more than 3,000 feet AGL. So the cruising altitude orders don't apply. So those are kind of the tricks that they get you on with these ones. So remember VFR, we add 500. Easterly, Newfies are odd. Newfies are in the east, so odd thousands plus 500 for easterly from 0 to 179. Even thousands plus 500 for westerly, and the wind will have an effect because these are based on magnetic track. So those are kind of your tricks there. So I was saying magnetic track, as opposed to what? There's a couple different types of track and heading, and they can be confusing sometimes on test questions. When you're actually going to plan across country, you'll probably use something like this. There's various different formats for nav logs out there. You'll probably punch in all your numbers onto something like this, and the thing is, though, when you write a test, you don't have access to this, and you're probably not going to remember all these boxes to write out on your test. So how does that all work? Well, we can distill this down a little bit. Some of these things, if we're just talking about like headings and tracks, directions, that kind of thing, let's just think about those things and not worry about things like right now the time and the gallons per hour and how fast we're going and the altitudes even and stuff like that. Let's just think about the track. There's a couple different factors that you're going to look at. So let's say we're going to plan across country. We're going to go from Owen Sound here, and we're going to go down to Stratford, let's say, and go talk to Andy down there at Stratford Airport. So from Owen Sound to Stratford, if you draw that line on your map, and then you measure it with your protractor, the number that you measure on the protractor, assuming that you're looking at the angle between these latitude longitude lines and our track, that angle we're going to come out to about 183 degrees. That's what's known as your true track. And then from that true track, you're going to do some kind of modification to it, and you're going to add wind. So let's say in this case, the wind's 220 at 10, and I will spare you the E6B calculation there. But when I put that in, what I find is for this true track, this wind, and my 172 flying at 90 knots, I get a true heading of 187. So the difference between the track and the heading is wind, right? So true track is the direction the airplane is moving over the ground. True heading is the direction the airplane is pointing. So that's a pretty important difference. But then we have all this other stuff over here. So we were talking about the cruising altitude orders being in magnetic. So how do you get to magnetic? Well, you have this variation here. You add in the variation, and then you get a magnetic heading. So in this case, if we go back to the map, it can be hard to find these variation lines, but here's one here kind of in the Kincardine area where it's saying 9 degrees west there. So that 9 degrees west variation, you will add west is best, east is least, so add west variation. You could also say it's 10 degrees. We're pretty close to this 10 degree line as well. But I think overall on our route, We almost crossed the 9-degree line. It's pretty close. You could go either way. But I put down 9 degrees variation there. So I add my 9 degrees variation, so my true heading goes from 187 to 196. And then the deviation, that is specific to the airplane. So you would look at inside the airplane, you'll have a little card right on the compass, little compass correction card. And what it would say is something like for 180 degrees, steer 183 degrees. And so what that means is if you want a heading of 180, there's a 3-degree error in the airplane's magnetism. There's electronics, there's metal, there's potentially errors in the compass itself. So for whatever reason, they weren't able to calibrate away that extra 3 degrees. So you would add that 3 degrees to get your compass heading. So lots of different kind of tracks and headings to go through to get the actual number to fly on the compass. And on the test, they'll definitely want you to go through this whole spiel, at least the individual parts. So the way that you can remember this for the test is separate your tracks from your headings, right? So that's the first thing. Know that tracks to headings, you're going to have to do your wind corrections, right? So your E6B corrections likely, or if you have a digital calculator, a digital flight computer, you can do it on that. And then from here we have TVMDC. TV makes dumb co-pilots. So you're gonna go true, variation, magnetic, deviation, compass to go through to get to the actual number to fly. So those are pretty big ones for test questions, I would say, because they do want you to be within typically a degree on a lot of these. What I find, just kind of generalizing, but what I find is they tend to give you a question which is kind of measuring on the map to start, and then they'll give you another number and then make you go through a process like this with it. So yeah. Okay. Somewhat related, when you're filling in a navlog, let me go back here. You've got lots of different time and distance and ground speeds and air speeds and fuel, and then fuel over time and that sort of thing. I want to look at some formulas to do with this. So the E6B flight computer is really good for doing these kinds of rates where you have so many miles or so many gallons in a given amount of time, and then you want to know how long is it going to take? What is the total amount of distance, total amount of gallons that it's going to take to do a given trip or something like that. So the E6B does that, but it can also be done just straight up on a calculator as well. So I want to show that. Okay. So the way to remember how to do this, or the way that I remember how to do this on a calculator, is we have a little speed triangle. So we take our distance, speed, and time. Distance, speed, and time. So if I finish it off with some extra lines, what I'll do is I'll write this out on my piece of paper, on my little note paper on the test. And let's say, or it doesn't have to be on the test. You know, if you're just doing some quick math, you forgot your E6B and you wanted to quickly figure out, oh man, I got 20 gallons. Is that enough enough to get me there, or you know, how long is this going to take, you know, with this this new route, this new distance, and that sort of thing. So let's say I wanted to figure out the time it's going to take. So what I would do is I would take my thumb on the page, and I would cover up the time. So then I'm left with distance and speed. Distance is just so happens to be over speed. So distance over speed, let's say I was going 100 miles, and the speed was 60. And I want to know the time because it's really windy today or something like that. Then I would pull out my handy dandy calculator. I'm gonna go 100 divided by 60. 1.66666. So basically 1.7 hours. And does that make sense? Well, we're going a little bit more than 50. 50 would be half of 100, right? So if we were going 50, 50 goes, you know, we would be going, yeah, if it was, yeah, if it was 50, then that would go in twice, but it's a little bit less than 2, right? It's a little bit less than 2 hours, so that does make sense, right? So if the airspeed was 50 in this case, then it would be 100 divided by 50. The answer would be 2. So a little bit more. We're going there a little bit faster. So instead of 2, it's 1.7. So that's kind of my reality check on that. So that makes sense, right? The way that you would do this on the E6B flight computer is you would take the speed first off, because you always start with the speed. You take that speed arrow and you would put it on the 60. My E6B won't come up on the screen, but you take the speed arrow, put it on the 60, and then you do the you look for 100 on the outer scale and read in to the inner scale, and you should get it probably says 16, not 1.6, but you would get to the answer that way. So that's kind of a rate one. Let's look at another example there. So again, I have my distance, speed, and time. In the case of a fuel flow, it wouldn't be distance up here. It would be you know, like total amount of fuel used, right? So let's think about one like that. So let me go fuel. So let's say that I was looking to figure out how much fuel am I going to burn. Let's say that my airplane burns 8 gallons an hour, right? So the 8 gallons an hour is kind of like a speed. It's a rate of fuel over time. So if I was looking to figure out how much fuel is it going to take to fly 2.5 hours, right? So I'm looking for the amount of fuel. I'm going to cover that up with my thumb. Now the S is next to the T. The rate of fuel burn is next to the time it's going to take. So that's going to be S times T. So I have 8 gallons an hour. What did I say? 2 hours? 2.5 hours? Let's say 2.5 hours. 2.5. So if you're using the calculator, it doesn't know hours and minutes. So you have to go 2.5, 2.5 hours, and type that in. So 8 gallons an hour times 2.5, 20 gallons, right? So you can see these can go through pretty quick on a calculator if you remember the speed triangle or the rate triangle here. So I kind of like doing those on the calculator like that. But the E6B will do all the same things. So again, for this problem, the speed or the rate of fuel burn is going to go under the arrow on the E6B. As long as you know the rate, you're going to line up the arrow with that. And then in this case, we have the time. Time is always on the inner scale on the E6B, and you would read across to the outer scale. And that would tell you the amount of fuel in this case. So yeah, there's kind of your rate ones, speed, distance, time sort of thing. Cool. Where I wanted to leave off, let me switch back to the map. Okay, so we're taking off on our trip, going from Owen Sound to Stratford, and you know, we wanna call ahead. We get in the air, and we wanna call them up and go, "Hey, are you guys open? I heard there's a global thing going on, and I wanted to just make sure I can get some gas and stuff like that." For whatever reason, you're not a very responsible pilot and you didn't pick up the phone. You wanted to do it all over the radio, right? So we're over Owen Sound. How high over Owen Sound would we need to be flying in order to reach the ground in Stratford? So by radio, how high would we need to be above the ground? Let's just assume, for the sake of argument, Owen Sound and Stratford are the same height. They're fairly close. How high above the ground do you need to get for that radio reception distance to get around the curve of the not flat Earth? What do you think? Take a wild guess. What do you think is the amount of altitude you'd need? I will prepare. Okay. So this one is one that I don't have a cool trick to use to calculate that. I've got a guess, and my guess is probably not too far off, but you know, just from my experience doing this sort of thing, it's about 70 miles away. I think we're gonna have to be a couple thousand, like maybe a little bit over 1,000, maybe 2,000 or something like that. So that's my guess, but I could be completely wrong. So like I say, the distance there, it's about 70 miles. In this case, it's telling me 71 miles to go from Owen Sound to Stratford. So when so the formula here that I'll just write out, this is where it gets to the, you kind of have to remember this one, and there's one specific number you really have to remember, which is 1.33. So if you remember 1.33, you should be able to solve this this problem here. So 1.33 times the square root of the altitude. (1.33) times the square root of the altitude. It's a bit of a mouthful, but that's the formula there. 1.33 times the square root of the altitude. So most calculators you should be able to do this on. It may need a scientific calculator in some cases, but funny enough, my scientific calculator I'm using in Windows here is actually, the scientific part doesn't work, but I got it in this standard mode. I got the square root button is what I need. So you find the square root button. It might, in this case, it has a little 2 above the squiggly line symbol here. I might have a little 2 up here. Sometimes it doesn't. So that's the key. What I'm going to do is I'm going to throw some guesses in there and see the output that I got, because this formula will give me a distance. This will tell me how many miles the reception will be, right? So remember, the number to beat is 71 miles for this route. Let me do the 2-finger sort of deal here. So this route's 71 miles, and so that's the number to beat. So I'll start with let's start with 1,000 feet. See how close we are. So 1,000 feet, square root of that, because remember, square root of the altitude. So square root of 1,000 feet gives me 31 and change, times 1 point. Whoops, messed it up. 1,000 square root of 1,000 times 1.33. Square root of 1,000 times 1.33 equals 42 and a bit. So not quite gonna make it. So our destination, 70 miles away, we'll get 42 and a bit. We'll get a little bit past Hanover there, it looks like. There's 40, 41, 42. Yeah, so we'll get a little bit past Hanover. Might almost reach Wingham. You know, might be a little bit shaky, but if someone had an antenna up on a pole or something, you might reach Wingham. But that's about it. So not quite making it there. Okay, so 1,000 didn't work. Let's do 1,500. 1,500 feet. Sorry, the square root of 1,500 feet. 1,500 square root times 1.33. 51 miles. Okay, back to the map. 51 miles, 51 miles. There's 51. Man, didn't make a whole lot of difference with that extra 500 feet. Okay, back to the calculator. Let's try 2,000. Square root times 1.33. 59 miles. Seems to be diminishing returns. It's not giving me a whole lot more, but let's take a look here. So 4, 5, 6, 7, 8, 59 miles right there. Still not quite making it. Okay, let's try 3,000. 3,000 feet. Surely 3,000 square root of that times 1.33. 72. What was the number to beat? It was 71. So 72 should just barely get us there. That's what I would say is kind of right. You know, this is a theoretical maximum too, right? So if the number came out to 3,000 and gave you an extra mile, great. Because think about the real world in here. There's some terrain in between here and there. 3,000 might be enough, might not be. That's kind of the theoretical maximum, right? But it would probably work. So here's 72 right there. So just a little bit past our destination there. So that's the reception distance. Now, this was assuming I'm trying to reach the ground in Stratford. Let's say that the apocalypse hits and there's an airplane that you sent a secret text message to, and you said, "Hey, get in the air at this time, and I'm gonna radio you my top secret message, and I want you to get it." How high would the airplane in Stratford have to be, and how high would we have to be in order to get the signal from us to them, right? So it gets a little more tricky, but it's just kind of one extra level to think about. So back to our formula here. If I just kind of modify this a little bit, I'm gonna add stage. Okay, so we had the square root of the altitude times 1.33. If we add another altitude, we just got to square root that as well. right? So the altitude for the transmitter and the altitude for the receiver, square root both of them, then add them together, and then times 1.33. So let's run through one of those. So let's take a guess again. You know, we have 2 airplanes in the air now, so we won't have to be 3,000 feet. We'll be able to get reception lower than that. So let's start with 1,000 feet. Let's see if we could both be at 1,000 feet. So I take 1,000, square root of that, gives me 31 and change, plus another 1,000, square root of that. You can see in my little thing up here. Let me make this a little bigger. Stand by. Just gonna make it so you can actually see the little window there a little closer. There we go. Okay, so just above the 0 here, it gives you a little record of what you just did. So 1,000 square root, 1,000, and so when I then go square root again, you can see square root of 1,000 plus the square root of 1,000. So that is what I wanted to do, and then multiply that whole thing. So the answer to that, by the way, comes to 63 and change. Multiply that whole thing by 1.33, and it gives me 84. So that's quite different. With 2 airplanes at 1,000 feet, I can get way past Stratford there. So if there's someone in the circuit in Stratford, you'd definitely be able to get reception to them. Quite strong reception, likely. So there's 84 miles right there. Almost to someone in the circuit in London, you'd be able to reach at 1,000 feet. Okay, so let me go back to more trial and error and trying to figure out a little bit lower down, maybe 800 feet. I wonder if we could reach them at 800 feet. So square root of 800 plus square root of 800, and again, remember the formula here. So I'm doing 800 square root plus 800 square root. I'll figure out what that is and then multiply the whole thing by 1.88. So that's what I'm doing there. Okay, square root of 800 plus the square root of 800. Result is 56 and change times 1.33. There you go, 75. So again, I think it was, what would we say? It was 71 miles to Stratford, so 75 would get us there. So just, it's probably a little bit lower than that is kind of the theoretical limits, but 75 would get us there. So it's kind of just under 800 feet. Let's even, I'm gonna be real specific. Let me see if 750 feet would get us there. 750 square root plus 750 square root. That looks right. Result of that is 54 and change times 1.33. 72. There you go. Yeah, so it's about 750 feet. If we were 750 feet in the circuit, we could reach an airplane in the circuit in Stratford. So that's kind of neat. That's totally been my experience. Like I hear guys over in kind of the Peterborough area in the circuit quite commonly. So, you know, I'll be in the circuit and maybe they're on approach to Peterborough. They're a little bit further away, like 100 miles. But maybe there's someone that's a little bit higher, like 1,500 feet or something like that, coming into Peterborough. We'll hear them there. What about another one like Tilsonburg? Sometimes I hear guys in the circuit at Tilsonburg. Yeah, Carol, did you do it there? Was it did it still work at 700? I haven't tried this one. 700 square root plus 700 square root times 1.33. Oh yeah, That'd be close. You might get a little scratchy something get through at 700 feet. It's real close. Okay, so we're going to Tilsonburg now. Tilsonburg is exactly 100 miles from Owen Sound. So Tilsonburg, I believe they are on Owen Sound's frequency because I hear them quite often. Yeah, they're on 123.0 down there in Tilsonburg. So we hear them once in a while. I don't normally hear guys that are saying like, okay, now we're on downwind, now we're on base, now we're on final. Sometimes, but not really when I'm in the circuit. I don't tend to hear that. And that makes sense because I think we just came up with, wasn't the number like 85 or something like that for the circuit there. Let me run that again. We're at 1,000 feet above the ground. Square root of that plus 1,000 feet above the ground. Oh, whoops. 1,000 feet square root plus 1,000 feet. And the square root of that. Square root of 1,000 plus the square root of 1,000 is 63 and change times 1.33. And yeah, so it's just under 85 miles. If we're in the circuit and another airplane's in the circuit, you'll hear them about 85 miles away, which has been my experience. I don't really hear guys, like I say, turning downwind, base, and final in Tilsonburg, but I will hear people on approach into Tilsonburg. So let's maybe think about this formula here again. It doesn't have to be the same altitude. So far I've done the same altitude on the first and on the second number here, but it will also work if it's different altitudes. So let's say we're in the circuit here at 1,000 feet, and the guys in Tilsonburg are in the say someone's joining the circuit and they're more like 2,000 feet. 1,000 square root of 1,000 plus the square root of 2,000. That's what I'm gonna do next here, and give that a try. See if I can hear someone 2,000. So 1,000 feet, that's us in the circuit, and plus we're listening to someone on approach into Tilsonburg. They're descending to join the circuit. They're at 2,000 feet. Will we be able to hear them? Gives me 76 and change to do 1,000 square root plus 2,000 square root times 1.33. Just barely, right? And that's kind of that was my hunch. Is it was around 2,000 feet. You can still hear guys into Tilsonburg. So up in Owen Sound, what I tend to hear is like, someone will be like 2,500, maybe 3,000 feet above sea level, on a descent into the circuit, and that's the last call I hear, because they're just a little too far away to get much more than that. So yeah, there's the reception distances there. So cool. Okay. I mixed up all my screens. That's all I got for tonight, guys. Thanks for coming out and hanging out and thinking about math and and seeing that math can be cool too. Yeah, let me know in the chat and in the comments if there's any formulas that give you trouble for sure. Kitty's sleeping actually, but way over there. Can't zoom in that far. Yeah, thanks guys for stopping by and chatting, and yeah, we will see you again next Friday, and plan on 7 o'clock again for something else, and go from there. So yeah, thanks guys. We'll see ya.